Deep in the space that separates the worlds of our solar system, 6 floating machines are preparing to witness something that has never before occurred in the history of space exploration. It's an October evening in the year 2025, and as the Earth turns toward nightfall, these spacecraft are adjusting their instruments toward a specific point in the Martian sky. The visitor they await does not belong to our solar system. For billions of years, it has traveled between the stars, carrying with it the chemical and physical secrets of worlds orbiting distant suns. Its name is 3I divided by Atlas, and in just a few hours, it will reach its closest approach to the red planet. Hello and welcome to our journey through the most extraordinary encounter of the year 2025. Tonight, we explore how 6 spacecraft around Mars are preparing to be unique witnesses to the approach of the interstellar Comet 3I divided by Atlas. Before we delve deeper into this cosmic coordination, take a moment to get comfortable wherever you may be listening, perhaps in bed, during a quiet evening walk, or in a peaceful moment of your day. If stories like this help you relax and discover new wonders, consider subscribing or liking this program. It helps more curious minds connect with these relaxing explorations. Now, let your thoughts drift as we explore this perfect dance between human technology and a cosmic visitor. What makes this encounter truly special is not just the rarity of the approaching object. It's the fact that for the first time in history, humanity has a complete fleet of robotic observers already positioned in the exact place where the most significant event will occur. It wasn't planned this way. There was no grand prior coordination to place these spacecraft in position. Simply, the universe conspired to have our most sophisticated machines in the right place at the right time. Mars Express, the veteran European spacecraft that has orbited Mars for over 20 years, will be the first to adjust its instruments. Its high-resolution stereoscopic camera, known as HRSC, has photographed every crater, every canyon, and every dune on the red planet. Now, those same sensors that have captured Martian beauty are preparing to document something that comes from much farther away. The sister spacecraft to Mars Express, the ExoMars Trace Gas Orbiter, brings complementary capabilities. Its CASSIS camera system was designed to study the Martian atmosphere with microscopic precision. The European scientists who designed these instruments never imagined that one day they would use them to analyze the gases escaping from a comet born next to another star. On the American side, the Mars Reconnaissance Orbiter represents the pinnacle of planetary observation technology. Its HiRISE instrument, the most powerful telescope ever sent to another world, can discern details on the Martian surface the size of a desk from a distance of 186 miles. When this optical colossus focuses on 3I divided by Atlas, it will offer images with a clarity that no ground-based telescope could match during this period. But the observation capabilities are not limited to the spacecraft orbiting Mars. In deep space, sailing toward the gas giant Jupiter, the European Space Agency's JUICE mission is in a unique position. Its Janus and Magus instruments were calibrated to study the icy moons of Jupiter. But over the next few days, these sophisticated systems will become the most privileged eyes to observe the behavior of 3I divided by Atlas during its perihelion. NASA's Psyche spacecraft, originally intended to explore the asteroid 16 Psyche in the asteroid belt, will also contribute observations. Its current trajectory places it in an advantageous position to capture data from a completely different angle, providing a three-dimensional perspective of the event. Engineers from the European Space Agency and NASA have worked for weeks to coordinate these observations. It is not a simple task. Each spacecraft has its own power limitations, its own communication windows with Earth, and its own mission schedules that must be maintained. However, the scientific importance of this moment has united teams from different continents in a coordinated effort. The coordination requires temporal precision measured in minutes. When 3I Atlas reaches its closest approach point to Mars, at a distance of only 18.6 million miles, each spacecraft must be correctly oriented, with its instruments calibrated and ready to capture data. It's like conducting a symphony orchestra, where each musician is separated by millions of miles, and the music can only be performed once. Scientists at the European Space Operations Center in Darmstadt, Germany, have programmed command sequences that will execute automatically. From NASA's Goddard Space Flight Center in Maryland, United States, engineers are monitoring the communication systems that will allow the transmission of data back to Earth. It is a collaboration that transcends national borders, united by scientific curiosity. What makes this moment even more extraordinary is the temporal context in which it occurs. During these October days, 3I divided by Atlas is in solar conjunction. From an earthly perspective, this means that the comet is positioned directly behind the Sun when observed from our planet. Ground-based telescopes, no matter how powerful, cannot penetrate the solar glare to observe the interstellar visitor. This limitation makes the spacecraft the only human witnesses to this cosmic encounter. They are our eyes, when our own have been temporarily blinded. They are our hands extended toward the cosmos when distance and physics conspire against direct observation. The importance of this coordination extends beyond its immediate scientific value. It represents a pivotal moment in space exploration, where multiple missions designed for specific purposes to adapt to address an unforeseen scientific opportunity. It is the demonstration that modern space exploration works best as an interconnected network of complementary capabilities. Each spacecraft brings unique strengths. Mars Express offers stability and experience with over 2 decades of successful operations. ExoMars provides the most advanced technology for atmospheric analysis. The Mars Reconnaissance Orbiter contributes with unrivaled imaging capabilities. JUICE brings instruments designed to detect and analyze ices and complex organic compounds. The sum of these capabilities creates an observation platform that no single mission could match. It's as if humanity had accidentally deployed the most sophisticated interstellar observatory in history, distributed across millions of miles, but synchronized to the microsecond. The data these spacecraft will collect over the next 72 hours will fundamentally change our understanding of interstellar objects. For the first time, we will be able to observe one of these cosmic visitors from multiple perspectives simultaneously, something impossible from Earth, even under the best conditions. As the spacecraft prepare for their coordinated observations, scientific teams on the ground wait with bated breath. They know they are about to witness something that might not be repeated for decades. Interstellar objects are rare, unpredictable in their arrival, and even more unpredictable in their behavior as they approach our Sunday. In the coming minutes, these machines that humanity sent to explore other worlds will become our ambassadors to a visitor from the stars. Their sensors will record light that has bounced off ices formed in another solar system. Their spectrographs will analyze gases released by a nucleus that formed when our sun was just a young star in the spiral arms of the galaxy. The encounter is about to begin, and 6 pairs of robotic eyes are preparing not to blink during the most important spectacle of their mechanical careers. In this perfect moment of cosmic coordination, human technology and scientific curiosity meet a fragment of the wider universe, creating a symphony of discovery that will resonate through future generations. The spacecraft have confirmed that they are ready. The instruments have been calibrated. The antennas are pointed toward Earth, prepared to transmit what they will see. Somewhere between Mars and the Sun, 3I divided by Atlas continues its approach, unaware of the witnesses that await it, carrying secrets that will soon be revealed for the first time in human history. It's September 28th, 2025, and in the most prestigious observatories on the planet, astronomers are facing a frustrating reality. Humanity's most powerful telescopes, from the James Webb Space Telescope to the gigantic instruments on the ground in Hawaii and Chile, have become useless for observing the most fascinating object crossing our solar system this decade. The problem isn't technological. It's not a flaw in the mirrors or atmospheric interference. The cause of this temporary blindness is much more fundamental. Our own star has moved between us and 3I divided by Atlas, creating what astronomers call a solar conjunction. From our perspective on Earth, the interstellar comet has disappeared behind the sun's glare, as if the sun had drawn a luminous curtain to hide the most important show of the year. For the next 3 months, any attempt to observe 3I divided by Atlas from Earth will be like trying to spot a lit candle while looking directly into a stadium floodlight. This solar conjunction is not a random event. It's the inevitable result of the laws of celestial mechanics and orbital geometry. As 3I divided by Atlas approaches its perihelion, the closest point to the Sun in its hyperbolic trajectory, its apparent position in Earth's sky aligns dangerously close to the solar disk. Scientists have calculated that the comet's solar elongation, the apparent angular distance between the comet and the Sun as seen from Earth, will reach a minimum of just 3 degrees. To put this in perspective, it's like trying to observe an object placed just over 2 inches from a bright light bulb, while keeping your eyes about 3 feet away. The sunlight doesn't just blind our instruments, its charged plasma interferes with any signal the comet might emit. The solar plasma, that soup of charged particles that extends millions of miles from our star's surface, acts as an electromagnetic barrier that's almost impenetrable. Radio waves that could bounce off the comet's nucleus get distorted and are lost in this sea of interference. Visible light photons are completely drowned out by the solar glare, which outshines the comet by a factor of several billion. This limitation is nothing new for astronomers. For decades, they have faced similar periods of conjunction. When studying planets, asteroids, or spacecraft passing behind the Sun, typically, these events represent forced pauses in research, moments when scientists must wait patiently until the objects of study emerge from the other side of the solar glare. However, the case of 3I divided by Atlas is different for one crucial reason. The timing of its solar conjunction coincides precisely with the most important days of its passage through our solar system. October 29th, when it reaches its perihelion and is at its most active, will be exactly when it's least visible from Earth. This unfortunate timing means that ground-based telescopes won't be able to observe the moment when the comet's ices begin to vaporize intensely under the solar heat. They won't be able to measure the exact composition of the gases escaping its nucleus, and they won't be able to document how its tail develops and changes during the most critical hours of its activity. For astronomers on Earth, it's like arriving at the theater just as the most important act of the play begins, only to find that someone has turned out all the lights. The frustration is palpable in research centers around the world, where scientific teams have spent months preparing observation campaigns that now must be cancelled. At the Mauna Kea Observatory in Hawaii, Dr. Sarah Chen has spent weeks calibrating the spectrographs of the Keck telescope to analyze the chemical composition of 3I divided by Atlas. Her calculations show the comet should be at its point of maximum activity, precisely when it disappears behind the Sunday. It's a cosmic irony, she explains with resignation. The most scientifically valuable moment will be when we are completely blind. The situation is similar at the ALMA Observatory in Chile, where radio astronomers had planned to study the comet's molecular emissions. The 66 radio telescopes of ALMA, working together, could detect specific molecules in the comet's coma with extraordinary precision. But not even this network of ultra-sensitive instruments can compete with the interference from solar plasma. The problem extends beyond Earth-based telescopes. Even space probes located at Lagrange points, those gravitationally stable regions where various scientific missions maintain permanent observatories, face similar limitations. The SOHO Observatory satellite, which has studied the solar corona for more than 2 decades from the L1 point, could theoretically detect 3I divided by Atlas, but only as a faint silhouette against the coronal glare. This temporary blindness for humanity creates an unprecedented situation in modern astronomy. For the first time in our scientific history, the most significant event related to an interstellar object will occur completely outside of our direct observational reach from Earth. Computer models suggest that during its perihelion, 3I divided by Atlas will undergo dramatic transformations. Its nucleus, composed of ices that have remained frozen for billions of years, will begin to sublimate rapidly under the intense solar radiation. This sublimation will release gases that haven't interacted with starlight since they formed in another solar system. The comet's coma, the diffuse atmosphere surrounding it, could expand to a diameter of several million miles. Its tail, dragged by solar radiation pressure and the solar wind, could stretch for tens of millions of miles in the direction opposite the Sunday. All this will occur while it remains invisible to us. Scientists have calculated that the comet's brightness could increase by several orders of magnitude during its perihelion. If it were visible, it could temporarily become one of the brightest objects in the night sky. But that brilliance will be completely hidden behind the solar curtain. The duration of this solar conjunction depends on the specific geometry of the comet's orbit and the Earth's position in its annual journey. Calculations show that 3I Atlas will not emerge from the solar glare until early December, at which point it will have already passed its perihelion and begun its journey back into interstellar space. When it is finally visible again from Earth, it will be a considerably less active object. Its nucleus will have released much of its volatile material, its coma will have started to shrink, and its tail, though possibly still impressive, will be in the process of dissolving. The most dramatic moments of its encounter with our Sun will have been recorded only in the memory of the cosmos. This situation highlights a fundamental reality of astronomy. We are limited by our specific position in the solar system. Unlike other sciences that can control the conditions of their experiments, astronomers must accept the circumstances the universe presents. We are observers, not directors of the cosmic show. However, this earthly limitation makes it all the more valuable to have our spacecraft distributed throughout the inner solar system. While the Earth remains blind, our robotic eyes keep vigil. They are the ones that will document these historic moments, the ones that will capture the data that will allow future generations to understand what happens when an interstellar visitor experiences the intimate embrace of our star. Earth's solar blackout is not a failure of our technology or a limitation of our instruments. It is simply a cosmic reminder that despite all our advances, we are still observers situated at a specific point in space, subject to the same physical laws that govern the motion of planets and stars. On this occasion, that limitation becomes the perfect opportunity for our spacecraft to demonstrate their true worth, as extensions of human curiosity into regions of the cosmos where our physical eyes cannot reach. If you could shrink the most advanced digital camera in your phone to the size of a grain of sand, it still wouldn't come close to the optical precision of the instrument currently orbiting Mars, preparing to capture the most detailed images ever taken of an interstellar comet. Its technical name is HiRISE, an acronym for High Resolution Imaging Science Experiment, but the engineers who built it simply call it the Colossus. About 370 miles above the Martian surface, the Mars Reconnaissance orbiter has maintained a stable orbit for nearly 2 decades. Its original mission was to photograph the surface of the red planet in unprecedented detail, identifying safe landing sites for future missions, and studying Martian geology from a perspective that no terrestrial rover could match. The HiRISE telescope it carries on board represents the culmination of decades of development in space optics. Its primary mirror, polished to a precision of 1/10,000th the thickness of a human hair, has a diameter of about 20 inches. This may seem modest compared to giant ground-based telescopes, but in the context of space, where every ounce counts and where vibrations must be minimized as much as possible, it's an engineering masterpiece. The resolution this instrument can achieve defies intuitive understanding. From its orbital altitude, it can distinguish objects on the Martian surface the size of a desk. Its CCD detectors, cryogenically cooled to minimize electronic noise, can capture images. With an effective resolution of about 1 foot per pixel, it's like having an eagle's view magnified 1,000 times. For years, HiRISE has been Mars's most faithful visual chronicler. It has photographed avalanches of frozen carbon dioxide tumbling down Martian cliffs, documented the formation and evolution of new impact craters, and captured images of rovers on the surface so detailed that you can see their wheel tracks in the Martian dust. But now, for the first time in its long operational career, HiRISE is preparing to look beyond Mars. The engineers at the University of Arizona, who operate the instrument from Tucson, have reprogrammed its observation sequences for a completely different target, a visitor from the stars. The transition is not simple. HiRISE was designed to photograph a static planetary surface, where targets remain in fixed positions relative to the spacecraft's orbit. Photographing a moving comet requires a completely different kind of pointing accuracy, calculated not just in terms of current position, but of trajectory prediction. Mission controllers have had to develop new tracking algorithms. Comet 3 divided by Atlas is moving at over 124,000 miles per hour as it approaches the Sunday. From the perspective of the Mars Reconnaissance Orbiter, this means the comet crosses the telescope's field of view in a matter of seconds. It's like trying to photograph a bullet in flight using a telescope designed to look at mountains. The optical setup of HiRISE includes 14 CCD detectors arranged in a line, each specializing in different wavelengths of light. 10 of these detectors capture images in red light, providing the maximum spatial resolution. 2 additional detectors work in blue-green light, offering information about the composition of the observed surface. 2 infrared detectors complete the set, allowing for analysis of temperature and mineral composition. When HiRISE focuses these 14 electronic eyes toward 3 divided by Atlas, each detector will capture a slightly different perspective of the comet. The combination of all these images will create not only a photograph of extraordinary resolution, but also a multispectral analysis that will reveal details about the surface composition of the comet's nucleus. The technical challenges go beyond simple pointing and tracking. The exposure must be calculated with pinpoint accuracy. Too short, and the image will be too dark to reveal details of the nucleus. Too long, and the comet's motion will cause blurring that will destroy the resolution for which HiRISE is famous. Engineers have developed a technique called motion compensation, where the entire spacecraft rotates slightly during the exposure to keep the comet centered in the telescope's field of view. It's a maneuver that requires coordination between the propulsion systems, the navigation gyroscopes, and the pointing control, all synchronized with microsecond precision. The distance between the Mars Reconnaissance Orbiter and 3 divided by Atlas during the closest approach will be approximately 18.6 million miles. At this distance, even the exceptional resolution of HiRISE will provide only a few pixels for the comet's nucleus. However, those few pixels will contain more information about an interstellar object than we have ever had. Each pixel of the resulting image will represent a surface of several miles on the comet's nucleus. But the information won't be limited to just shape and size. HiRISE's different spectral detectors will reveal variations in color and composition across the nucleus's surface. The darker regions could indicate complex organic materials, while the brighter areas could signal the presence of exposed ices or specific minerals. The comet's coma, that diffuse atmosphere of gas and dust surrounding it, will also be visible to HiRISE. Although this gaseous envelope is too faint to be detected by ground-based telescopes during solar conjunction, HiRISE's sensitivity and its advantageous position will allow it to map the structure and distribution of the coma in unprecedented detail. Scientists hope to be able to distinguish jets of gas emanating from specific points on the nucleus. These jets, caused by the sublimation of ices under solar heating, could reveal the comet's internal structure and the distribution of volatile materials inside. Each jet would act as a window into the nucleus's composition, showing what types of ices and compounds were formed in the comet's original star system. The image processing technique has also been adapted for this unique target. The algorithms normally used to enhance features on the Martian surface have been modified to optimize the detection of cometary structures. Special filters have been developed to separate the light reflected by the solid nucleus from the diffuse emission of the gaseous coma. The science team has prepared multiple observation sequences for different scenarios. If 3 divided by Atlas turns out to be brighter than expected, they will use shorter exposures to avoid saturating the detectors. If it's fainter, they will combine multiple images to increase the signal-to-noise ratio. This operational flexibility is crucial when observing an object whose properties are largely unknown. The data that HiRISE captures during these historic days will be transmitted to Earth. via the Mars Reconnaissance Orbiter's high-gain antenna. Each complete image contains gigabytes of information, requiring several hours of continuous transmission to reach the receivers of the Deep Space Network in California, Spain, and Australia. Once on Earth, these images will go through a calibration and processing procedure that will take weeks. Scientists at the University of Arizona will work in collaboration with Comet experts from institutions around the world to extract every bit of scientific information from this unique data. HiRise's images of 3 divided by Ibarra Atlas will not only be the most detailed ever taken of an interstellar comet, they will represent a historic moment where technology designed to explore one world is adapted to study a visitor from the stars, demonstrating the versatility and lasting value of our robotic eyes in the cosmos. In the coming days, when HiRise focuses its gaze on 3 divided by Ibarra Atlas, it won't just be taking pictures, it will be writing the first visual chapter of our understanding of what objects from other star systems really look like. Page by page, pixel by pixel. What secrets could be revealed by the light that has bounced off ices, formed billions of years ago next to a distant star? This question, which would have seemed purely philosophical just a few decades ago, can now be answered thanks to the most sophisticated spectrographs ever sent into interplanetary space. Instruments that are preparing to dissect every photon emitted by 3 divided by Ibarra Atlas during its historic encounter with our solar system. Spectrographs are the universe's chemical detectives. While our eyes see only colors, these instruments break down light into its fundamental components, revealing the unique signatures that each element and molecule imprints on the electromagnetic spectrum. It's as if they have the ability to read the chemical history written in every ray of light that reaches them. Aboard the veteran Mars Express, the Omega spectrograph has spent more than 2 decades mapping the mineral composition of Mars. Its full name, Observatoire pour la minéralogie, l'eau, les glaces et l'activité, perfectly describes its mission: to identify and quantify the materials that make up alien worlds. By analyzing the infrared light they reflect, Omega works by splitting infrared light into 352 different spectral channels, each tuned to detect the specific signature of different minerals and compounds when sunlight bounces off an object's surface and reaches Omega. Every mineral present leaves its spectral, unique fingerprint in that reflected light. During its long career studying Mars, Omega has identified hydrated clays that suggest a wet past, sulfate minerals indicating ancient volcanic activity, and ices of water and carbon dioxide in the polar regions. Now, these same detectors are preparing to analyze materials that didn't form in our solar system. The transition to cometary observation presents unique challenges. While Mars has a stable, solid surface, 3I divided by Atlas is surrounded by a dynamic atmosphere of gas and constantly evolving dust. The spectrographs must separate the signals coming from the solid nucleus from those originating in the gaseous coma that surrounds it. Scientists at the Institute of Space Astrophysics in Orsay, France, who operate Omega, have developed special processing techniques for this observation. They will use algorithms that can distinguish between the light reflected by the solid surface of the nucleus and the light emitted by excited gases in the coma. This is a crucial distinction because each type of signal reveals different information about the comet. The surface of the nucleus, composed mainly of ices mixed with dust and organic materials, will reflect sunlight in specific patterns that Omega can interpret. Each type of ice, whether it's water, carbon dioxide, carbon monoxide, or methane, has a distinctive spectral signature in the near-infrared. Simultaneously, aboard the ExoMars Trace Gas Orbiter, the NOMAD spectrograph is preparing for a complementary task. NOMAD, an acronym for Nadir and Occultation for Mars Discovery, was originally designed to detect trace gases in the Martian atmosphere, specifically looking for methane and other compounds that could indicate biological activity. NOMAD's extraordinary sensitivity for detecting gases in minimal concentrations makes it the perfect instrument for analyzing the coma of 3I divided by Atlas. While Omega studies the solid surface, Nomad will concentrate on the gases escaping from the nucleus under the influence of solar heating. The Belgian and British engineers who built Nomad equipped it with 3 distinct spectral channels. The solar occultation channel operates in the near-infrared, perfect for detecting water vapor and carbon dioxide. The nadir channel works in the mid-infrared, ideal for identifying methane, formaldehyde, and other organic compounds. The ultraviolet visible channel can detect ozone, nitrogen oxides, and other photochemically active gases. The coordination between Omega and Nomad during the observations of 3I divided by Atlas will be crucial. Both instruments will observe the comet simultaneously, but from slightly different angles, due to the different orbits of their spacecraft. This stereoscopic perspective will allow scientists to create a 3-dimensional map of the gas distribution around the nucleus. The spectral data these instruments will collect during the encounter will provide the first direct measurement of the detailed chemical composition of an interstellar object. The relative proportions of different types of ice in the nucleus will reveal the physical conditions that existed in the protoplanetary disk, where the comet formed billions of years ago. Scientists expect to find significant differences between the composition of 3I divided by Atlas and that of comets native to our solar system. These differences could reflect variations in the chemistry of different stellar systems, the distances at which the comets formed from their parent stars, or the specific processes that occurred during the formation of their planetary systems. One of the most important measurements will be the deuterium to hydrogen ratio in the water vapor released by the comet. This ratio, known as D divided by H, acts as a fingerprint that reveals where and when the water formed. Water formed in different regions of the galaxy under different temperature and pressure conditions, exhibits characteristic D divided by H ratios. The spectrographs will also look for complex organic compounds in the comet's coma. Molecules like methanol, ethanol, formaldehyde, and acetaldehyde have been detected in comets from our solar system and are considered important precursors to prebiotic chemistry. Their presence in 3I divided by Atlas could suggest that the chemical processes that led to life on Earth also occurred in other stellar systems. The technique of emission spectroscopy will be especially valuable during the observation of 3I divided by Atlas. When the coma's gases are excited by solar ultraviolet radiation, they emit light at specific, characteristic wavelengths for each molecule. This emission is like a luminous signature that unequivocally identifies the presence of specific compounds. The science teams have prepared reference spectral libraries containing the known signatures of hundreds of different molecules. During the observations, the spectra captured from 3I divided by Atlas will be automatically compared with these references, allowing for the rapid and precise identification of the chemical components present. Processing the spectral data will require advanced computational techniques. The raw spectra must be corrected for atmospheric effects, calibrated using reference stars, and processed to remove instrumental noise. Only after these corrections will it be possible to extract the comet's true chemical abundances. The results of these spectral analyses will not only improve our understanding of 3I divided by Atlas specifically, but will also provide fundamental insights into the chemical diversity of interstellar objects. Every element detected, every molecule identified, every isotopic ratio measured will add a piece to the puzzle of how planetary systems form and evolve throughout the galaxy. In the coming hours, when Omega and Nomad focus their detectors on 3I divided by Atlas, they won't just be measuring chemical compositions, they will be reading a chemical book written billions of years ago, in another corner of the galaxy, now being deciphered for the first time by human curiosity and technology. Halfway between Mars and Jupiter, navigating the vacuum of deep space at a speed of 15 miles per second, the European Space Agency's JUICE spacecraft finds itself in a position that no engineer could have planned better, even if they had decades to calculate it. By sheer cosmic coincidence, this mission, destined to explore Jupiter's icy moons, has become the most privileged observatory for studying 3I divided by Atlas during the most critical moments of its encounter. With our Sunday JUICE, whose full name is the Jupiter Icy Moons Explorer, was launched in April 2023, with a clear mission to study the moons Ganymede, Callisto, and Europa to determine if their subsurface oceans could harbor life. Its complex trajectory, which includes multiple gravity assists from Venus and Earth, will take it to Jupiter in 2030, where it will spend at least 3 years exploring the Jovian system. But on the 29th of October 2025, JUICE will find itself in an extraordinarily favorable location to observe the perihelion of 3I divided by Atlas, while Earth remains blinded due to solar conjunction. And while the Martian spacecraft observe from a side-on perspective, JUICE will have an almost head-on view of the comet during its peak activity. The orbital geometry that places JUICE in this privileged position is a result of the immutable laws of celestial mechanics. The spacecraft follows a heliocentric trajectory that during these specific days in October positions it on the opposite side of the Sun, with respect to Earth, but in a direct line of sight to 3I divided by Atlas. This position offers unique observational advantages. While the Martian spacecraft will see the comet in profile, JUICE will observe it almost head-on during its approach to the Sunday. This head-on perspective will make it possible to study the structure and evolution of the comet's coma in a way that is impossible from other positions. On board JUICE are 11 state-of-the-art scientific instruments, many of which are perfectly suited for cometary study. The Janus camera system, developed primarily to photograph the surfaces of the Jovian moons, includes a wide-field and a narrow-field camera that can capture detailed images of 3I divided by Atlas from its advantageous position. Janus was designed to operate in the light conditions, extremely faint parts of the Jovian system, where sunlight is 25 times weaker than on Earth. This sensitivity to low light makes it an ideal instrument to detect and characterize the coma of Tsuchinshan-ATLAS, especially its outer regions where gas and dust are more dispersed. The MAGIS imaging spectrograph, another of JUICE's main instruments, adds sophisticated spectroscopic capabilities to the cometary observation mission. It can operate from the visible to the near-infrared, providing detailed information on the composition of both the nucleus and the comet's coma. The spectral versatility of MAGIS will allow it to identify different types of ices in the nucleus of Tsuchinshan-ATLAS, as well as the specific gases released during sublimation. Its 488 spectral channels can distinguish between water, carbon dioxide, carbon monoxide, methane, and dozens of other compounds with extraordinary precision. Engineers at the European Space Agency have had to carefully modify JUICE's operational plans to take advantage of this unforeseen scientific opportunity. The spacecraft was scheduled to perform routine instrument calibrations during this period, but these activities have been rescheduled to allow for dedicated observations of Tsuchinshan-ATLAS. Modifying mission plans is not a trivial task in deep space. JUICE operates on limited power provided by its 915 square-foot solar panels. At its current distance from the Sun, these panels generate only a fraction of their maximum capacity, requiring careful management of energy resources. Mission controllers at the European Space Operations Center have calculated observation sequences that maximize the scientific return while keeping the spacecraft in safe operational condition. This includes rotating JUICE to optimize both the orientation of its instruments toward Tsuchinshan-ATLAS and the orientation of its solar panels toward the Sunday. Communicating with JUICE during the observations presents additional challenges. The spacecraft is more than 310 million miles from Earth, which means radio signals take almost 30 minutes to travel in each direction. This makes real-time control impossible, requiring all observation sequences to be programmed and executed automatically. The scientific data collected by JUICE during these observations will be transmitted back to Earth, using its 10-foot diameter high-gain antenna. However, the vast distance means the data transmission rate will be relatively slow, requiring weeks to fully download all the observations of Tsuchinshan-ATLAS. One of JUICE's most valuable contributions will be its ability to observe the temporal evolution of the cometary activity during perihelion. While other spacecraft can provide snapshots of Tsuchinshan-ATLAS, at specific moments, JUICE will be able to document how the comet's coma changes hour by hour. during its peak activity. Scientists hope that JUICE will capture the exact moment when the comet's sublimation activity reaches its absolute peak. This moment, predicted by computer models but never directly observed in an interstellar object, could reveal fundamental differences in how materials formed in other star systems respond to solar heating. JUICE's unique perspective will also allow for polarimetry studies of the comet. The light reflected and emitted by Tsuchinshan-ATLAS will be partially polarized, and the analysis of this polarization can reveal information about the size, shape, and composition of the dust particles in the coma. The submillimeter wave instrument, an instrument on JUICE designed to study Jupiter's atmosphere, can also contribute to the cometary observations. This instrument can detect specific molecular transitions in the coma of Tsuchinshan-ATLAS, providing precise measurements of the abundances of different chemical species. The results from the observations by JUICE will be especially valuable when combined with simultaneous data from the Martian spacecraft. Triangulation between multiple observation points will allow for determining the three-dimensional structure of the comet's coma. With unprecedented precision, European scientific teams have established protocols for the rapid exchange of preliminary data between JUICE and the Martian missions. This coordination will allow for real-time adjustments to observation strategies, optimizing the scientific return from the event. The position of JUICE during the perihelion of Tsuchinshan-ATLAS also offers a unique opportunity to study the interaction between the solar wind and the comet's coma. From its perspective, JUICE can directly observe how solar radiation pressure shapes and accelerates the comet's tail. In the coming days, while JUICE maintains its lonely vigil in deep space, its instruments will document moments that may not be repeated for generations. Its fortuitous position makes it the most comprehensive chronicler of how an interstellar visitor experiences the intimate embrace of our star. When the data from JUICE finally reaches Earth and is processed by scientists around the world, it will provide the most complete view ever obtained of an interstellar object during its most active phase. It is a perfect demonstration of how space exploration, planned for one purpose, can be adapted to take advantage of unforeseen scientific opportunities that arise from the complex dance of celestial bodies. In the absolute silence of the vacuum of space, where no sound can travel, the spacecraft observing Tsuchinshan-ATLAS maintain a constant dialogue with Earth through radio waves that travel at the speed of light. These invisible conversations, transmitted by antennas, with exquisite directional precision, carry the most important discoveries about interstellar objects ever collected by humanity. The spacecraft's antennas are masterpieces of precision engineering. The high-gain antenna of the Mars Reconnaissance orbiter, with its 10-foot diameter parabolic design, can focus radio signals with the precision of a laser, directing beams of information across hundreds of millions of miles to reach terrestrial receivers that are no larger than football fields. This antenna operates mainly in the X-band, using frequencies around 8 GHz. The choice of this frequency is not accidental. X-band waves efficiently penetrate the atmospheres of Earth and Mars, suffer minimal interference from interplanetary plasma, and can carry large volumes of scientific data with minimal distortion. Mars Express uses a slightly different communication system, with a 5.4-foot high-gain antenna that can transmit in both X-band and S-band. The frequency flexibility allows operators to optimize communications according to the specific conditions of interplanetary space and the availability of ground receiving stations. The ExoMars Trace Gas Orbiter employs even more advanced communication technology. Its transmission system can switch between multiple frequencies and modulation schemes, automatically adapting to propagation conditions to maintain stable links even during solar storms or atmospheric interference. The data collected during the observations of Tsuchinshan-ATLAS must be carefully encoded before transmission. The encoding systems use error correction algorithms that can detect and correct corruptions introduced during the interplanetary journey. Without these systems, critical scientific information could be lost due to cosmic interference. Every high-resolution image captured by HiRISE contains gigabytes of information. At the transmission speeds available from Mars, which typically range from 1 to 10 megabits per second, Depending on the distance and planetary alignment, a single complete image can require several hours of continuous transmission. Spectrographs generate even larger volumes of data. Each spectral observation from Omega produces files containing information from 352 different spectral channels, each sampled at multiple spatial and temporal resolutions. The complete transmission of an observational sequence can extend over several days. The logistical challenge of handling these massive, active volumes of data requires careful coordination between multiple ground stations. NASA's Deep Space Network, with its main facilities in California, Spain, and Australia, provides 24-hour coverage to receive transmissions from spacecraft throughout the solar system. Each station of the Deep Space Network includes gigantic parabolic antennas, the largest of which is 230 feet in diameter. These antennas, built with a precision that allows them to detect signals trillions of times weaker than the light from a light bulb seen from the moon, can track spacecraft as Earth's rotation moves them across the sky. Receiving data from Jupiter presents additional challenges due to its great distance. The signals from JUICE are so weak when they reach Earth that they require long integration periods to extract useful information from the cosmic background noise. Engineers use signal processing techniques that can detect data patterns buried in seemingly random noise. The communication systems must also carefully coordinate the use of the radio spectrum. The frequencies used for space communications are internationally regulated to avoid interference with terrestrial services like radar, air navigation, and military communications. During the critical observations of 3I divided by Atlas, the spacecraft prioritized the transmission of scientific data, which is essential. The onboard automated systems can identify observations of greater scientific importance and transmit them first, ensuring that the most valuable data reaches Earth even if technical interruptions limit the available transmission time. Communication latency presents unique operational challenges. Radio signals travel at the speed of light, but even at this extreme speed, messages from Mars take between 4 and 24 minutes to reach Earth, depending on the relative positions of the planets in their orbits. This delay means that real-time control is impossible during critical observations. The operations teams must program command sequences that run automatically, relying on artificial intelligence on board to adapt to unforeseen conditions without ground intervention. The communication protocols include multiple redundancies to ensure that critical scientific data is not lost. Each important observation is transmitted multiple times using different encoding schemes, and, when possible, through different antennas and frequencies. The mission control centers constantly monitor the quality of communications. Sophisticated algorithms analyze signal strength, the error rate, and transmission efficiency, automatically adjusting parameters to optimize the flow of scientific data during special events. For events like the 3I divided by Atlas observations, extended shifts are established in the control centers to ensure continuous coverage. Specialist engineers remain on alert 24 hours a day, ready to intervene if technical problems threaten the reception of unique data. Coordination between different space agencies requires standardized communication protocols. The data from Mars Express, ExoMars, and JUICE use compatible formats that allow for integrated scientific analysis. Even though the spacecraft were built by different countries and organizations, the onboard data storage systems also play critical roles. Each spacecraft includes solid-state memory that can store observations until communication conditions allow for efficient transmission to Earth. This storage capacity acts as a buffer against temporary interruptions in communications. The ground networks that connect the receiving stations with the science centers use high-speed fiber optics to move data from the antennas to the laboratories where it will be analyzed. These links can transfer terabytes of scientific information in a matter of hours. In the coming days, as the spacecraft capture historic data on 3I divided by Atlas, their communication systems will work tirelessly to ensure these unique discoveries arrive safely on Earth. They are the invisible threads that connect our robotic eyes in the cosmos with human curiosity, transporting interstellar secrets across the void at the speed of light. It is 14:37 Coordinated Universal Time. on October 3, 2025. At this precise instant, calculated years in advance by the world's best specialists in celestial mechanics, 3I divided by Atlas reaches its point of closest approach to Mars, exactly 18,624,428 miles away. The numbers may seem abstract, but they represent an unprecedented historical moment. Never before in human history have we had a fleet of robotic observers strategically positioned to document the close approach of an object from interstellar space to one of our neighboring worlds. Aboard the Mars Reconnaissance orbiter, the automated systems have been running programmed observation sequences for weeks. The spacecraft has subtly adjusted its orbit, using small propulsion corrections to optimize its position during these critical hours. Each maneuver has been calculated to maximize observation opportunities while maintaining the orbital stability necessary for continued operations. The temporal precision required for this event defies common understanding. 3I divided by Atlas is moving at approximately 130,000 miles per hour during its approach to Mars. At this speed, a timing error of just 1 minute could shift the observations by more than 2,100 miles, potentially compromising the quality of the scientific data. Mission controllers have divided the optimal observation window into segments with military precision. Between 14 and 17 Coordinated Universal Time, each spacecraft will execute specific sequences designed to capture different aspects of the encounter. The coordination requires synchronization down to individual seconds. Mars Express begins its observations 3 minutes before the closest approach, using its Omega spectrograph to capture baseline data of the comet's composition, before Martian gravitational effects can influence its behavior. This baseline data will be critical for interpreting subsequent changes in cometary activity. The ExoMars Trace Gas Orbiter is concentrating on the detection of trace gases during the period of closest approach. Its NOMAD instrument is calibrated to detect even the most minute concentrations of volatile compounds that could be released due to heating from Mars's infrared radiation or tidal disturbances. The tidal forces that 3I divided by Atlas experiences during its approach to Mars are insignificant compared to those it will experience near the Sun, but they still represent the most intense gravitational influences that the comet has felt. During millions of years of interstellar travel, scientists speculate whether these forces could trigger the release of gases or detectable structural changes. The Mars Reconnaissance Orbiter is executing a high-resolution imaging sequence designed to capture 3I divided by Atlas from multiple angles as it passes the point of closest approach. The spacecraft's natural rotation during its orbit provides slightly different perspectives of the comet, effectively creating a rudimentary stereoscopic capability. The solar illumination of the comet during this period is optimal from the Martian perspective. 3I divided by Atlas is in a nearly full phase when observed from Mars, with its day side completely visible, and its coma illuminated from an angle that maximizes the contrast against the stellar background. The navigation systems of each spacecraft have been tracking the position of 3I divided by Atlas with increasing precision for days. The orbital predictions, initially based on ground-based telescopic observations, have been continuously refined using data from the spacecraft themselves, improving the pointing accuracy of the scientific instruments. The onboard navigation cameras, typically used to determine the spacecraft's orientation relative to reference stars, have been reprogrammed to track 3I divided by Atlas directly. This real-time tracking allows for automatic pointing corrections that keep the comet centered in the fields of view of the main instruments. During the moments of closest approach, each spacecraft is executing observations simultaneously, creating the first multispectral and multi-perspective study of an interstellar object ever conducted. The data collected during these critical minutes will provide unique insights into the structure, composition, and behavior of materials formed in another star system. The density of scientific data generated during this time window is extraordinary. In the span of 3 hours, the spacecraft will capture more information about 3I divided by Atlas than all the information gathered on previous interstellar objects combined. It is a moment of unprecedented scientific focus. Engineers have programmed multiple redundancies into the observation systems. If an instrument experiences technical failures, during the closest approach, backup systems are ready to activate automatically. The unique importance of this moment allows for no second chances. The conditions of interplanetary space during the approach are continuously monitored. Solar activity, which can interfere with instruments, sensitive instruments and communications, is at relatively low levels, providing ideal conditions for precision observations. Science teams on the ground are waiting in control centers around the world, monitoring real-time telemetry that confirms the operational status of each instrument. Although they cannot control the observations directly, due to the communication delay, they can verify that the programmed sequences are running correctly. The geometry of the approach also provides unique opportunities for precise astrometric measurements. The exact position of 3I divided by Atlas can be determined with extraordinary precision using the known positions of background stars, further refining our knowledge of its orbit and origin. During the closest approach, the detectors are capturing light that has traveled from the comet's nucleus for several minutes, light that bounced off ices formed billions of years ago under completely different physical conditions than those that exist in our solar system. The moments pass with chronometric precision. Each second records unique data. Each minute completes irreplaceable observational sequences. It is a scientific symphony executed by human-built machines, documenting the encounter between our neighboring world and a messenger from the stars. When the moment of closest approach finally passes and 3I divided by Atlas continues its trajectory toward the Sun, it will have left its mark on the digital memory of our spacecraft. The data captured during these critical hours will occupy terabytes of storage and will require years of analysis to extract all its scientific secrets. The closest approach of 3I divided by Atlas to Mars is not just an astronomical event. It is a pivotal moment in space exploration, where the precise coordination between multiple missions transforms a cosmic coincidence into the most significant scientific opportunity of the decade. Imagine if you could simultaneously observe the same object from 6 different perspectives, each equipped with instruments more sensitive than any ground-based telescope, and that this object was something you had never seen before, a fragment from another solar system. This observational capability, unprecedented, is generating types of scientific data that would be completely impossible to obtain from Earth, even under the best conditions. The fundamental advantage of having multiple spacecraft observing 3I divided by Atlas simultaneously lies in the capacity for spatial triangulation. When Mars Express captures an image of the comet from its orbital position, and simultaneously the Mars Reconnaissance orbiter photographs the same object from a different location, scientists can calculate distances, dimensions, and three-dimensional structures with extraordinary precision. This triangulation reveals the true architecture of the comet's coma in ways impossible from a single point of observation. The gases and dust surrounding the nucleus of 3I divided by Atlas do not form a perfect sphere, but rather complex structures influenced by the nucleus's rotation, its surface topography, and the uneven distribution of volatile materials within it. The spectrometers aboard different spacecraft simultaneously capture the comet's chemical signatures from different angles, revealing how the composition varies across the coma. This spatial variation in chemistry provides direct clues about the internal structure of the nucleus and the sublimation processes that release different materials from specific regions. The radial velocity data measured by instruments that can detect the Doppler shift of spectral lines show how the gases move within the coma. This kinematic information reveals the internal dynamics of the comet's atmosphere, including flow patterns, escape velocities, and the influence of the solar wind on the tail's evolution. Simultaneous measurements from multiple positions also allow for unique occultation studies. When 3I divided by Atlas passes between different spacecraft, it temporarily blocks the light of background stars. The analysis of how this light is attenuated and distorted as it passes through the coma reveals the density and distribution of particles with microscopic precision. The instruments on each spacecraft are calibrated to detect different ranges of the electromagnetic spectrum, effectively creating a distributed observatory with complementary capabilities. While HiRISE captures images in visible light with extreme resolution, Omega analyzes infrared signatures that reveal temperatures and mineral compositions, and NOMAD detects trace gases in parts per billion concentrations. This simultaneous spectral diversity provides a complete portrait of 3I divided by Atlas that no single observation could match. Scientists can correlate visible features in high-resolution images with specific chemical signatures, mapping the spatial distribution of different compounds across the comet. The temporal data captured during the coordinated observations reveal how 3I divided by Atlas changes hour by hour. Cometary activity is not constant but variable, with gas jets turning on and off as different regions of the nucleus rotate into sunlight. This temporal variability can only be documented with continuous, high-cadence observations. Polarization measurements of the light reflected by the comet, taken from multiple angles simultaneously, provide detailed information about the size, shape, and composition of the dust particles in the coma. These particle properties reveal conditions in the original protoplanetary disk where the comet formed. Light scattering studies from different observational geometries show how the coma of 3I divided by Atlas interacts with solar radiation. The scattering patterns are sensitive to the microscopic structure of the dust particles and can reveal if these materials have different properties from those found in comets from our solar system. The coordinated observations also capture transient phenomena that could be missed in single observations. Sudden outbursts of activity, the formation of new jets, or structural changes in the tail are short-lived events that require continuous monitoring from multiple perspectives to be fully characterized. Magnetic field data, although limited due to the large distances involved, can be detected indirectly through the interaction between the solar wind and ions in the comet's coma. This interaction creates subtle electromagnetic signatures that can be measured by sensitive instruments aboard the spacecraft. High-precision gravimetric measurements taken by analyzing small perturbations in the spacecraft's orbits can detect the mass of 3I divided by Atlas with extraordinary accuracy. This direct mass determination is crucial for calculating the comet's density and inferring its internal structure. Isotopic analyses of the gases released by the comet provide information about the physical conditions that existed in the protoplanetary disk where it formed. The ratios of different isotopes are like fingerprints that reveal temperatures, pressures, and chemical processes specific to the original stellar system. Ablation data, which measure how much material the comet is losing per unit of time, can only be accurately determined through prolonged observations from multiple perspectives. This mass loss rate reveals how the interstellar objects to solar heating compared to native comets. The combined angular resolution of multiple instruments working together overcomes the physical limitations of any single telescope. Aperture synthesis techniques, adapted from radio astronomy, can combine observations from different spacecraft to effectively create a virtual telescope the size of the inner solar system. Chemical composition studies reveal not only what elements are present in 3I divided by Atlas, but also their relative abundances and chemical states. These measurements provide direct insights into the planetary formation processes that occurred in the stellar system where the comet was born. The data collected during these unique days will require years of analysis by international science teams. Each individual observation is valuable, but the true scientific power emerges from the combination and integration of all the simultaneous data, creating a multi-dimensional understanding of an interstellar object that transcends any previous study. This unique deep space data not only expands our knowledge of 3I divided by Atlas specifically, but also establishes the techniques and methodologies we will use to study future interstellar visitors. They represent the dawn of a new era in interstellar astronomy, where multi-instrument coordination transforms individual observations into revolutionary discoveries. How do organizations from different continents, with distinct institutional cultures and independently developed technical systems, manage to coordinate the most complex observation of an interstellar object ever attempted? The answer reveals a fascinating facet of modern space exploration: science diplomacy in action. At the European Space Operations Center in Darmstadt, Germany, it's 3 in the morning on October 4th, but the night shifts are fully active. The controllers for Mars Express and ExoMars are monitoring screens that show the status of their spacecraft in real time, coordinating via encrypted communication links with their NASA counterparts. At the Jet Propulsion Laboratory in Pasadena, California, where it's 6 p.m. the previous day, this temporal coordination transcends time zones and language barriers. The communication protocols, developed over months of preparation, ensure that critical information is shared instantly between teams that speak English, German, French, Italian, and Dutch, but who use the universal language of science and space engineering. The cooperation agreements that allow for this coordination were built on decades of mutual trust between space agencies. The European Space Agency and NASA have collaborated on dozens of missions, from the International Space Station to the missions to Mars, creating institutional frameworks that facilitate the rapid exchange of data and resources. The exchange of scientific data during the 3I divided by Atlas observations operates under protocols established by the Committee on Space Research, an international organization that defines standards for space science cooperation. These standards ensure that data collected by European instruments can be immediately analyzed by American scientists and vice versa. The control centers use redundant communication systems that include satellite links, fiber optic connections, and backup radio networks. This redundancy ensures that if a link fails during critical observations, the coordination can continue without interruptions that could compromise the mission's scientific success. The temporal synchronization, N7 between different control centers requires reference to atomic clocks maintained by national standards organizations. Coordinated universal time provides a common reference that allows events scheduled to the second to occur simultaneously on spacecraft controlled from different continents. The scientific teams leading the 3I divided by Atlas observations include researchers from universities and research institutes in more than 12 countries. This international diversity brings specialized expertise from different scientific traditions and methodological approaches, enriching the analysis of the unique data that is being collected. The differences in institutional cultures between European and American organizations were carefully navigated during planning. European agencies tend toward more consensus-based and deliberative approaches, while NASA operates with more centralized command structures. The collaboration protocols respect these differences while maintaining operational efficiency. The legal aspects of international cooperation in space are governed by the Outer Space Treaty of 1967, which establishes principles for peaceful cooperation in space exploration. The 3I divided by Atlas observations operate completely within this international legal framework. The exchange of sensitive technical information between agencies requires specific technology transfer agreements. Although most scientific data is shared freely, certain aspects of instrument capabilities and operational techniques are subject to export controls that must be carefully navigated. The budgets for the coordinated observations come from multiple national sources, but the costs are implicitly shared through in-kind contributions. ESA provides observation time on its spacecraft, while NASA offers the capabilities of the Deep Space Network and expertise in data processing. The resulting scientific publications from these observations will follow co-authorship protocols that reflect the contributions of different national teams. The main papers will include authors from all the participating reason institutions, ensuring that scientific credit is distributed appropriately. Students and young researchers from multiple countries are participating in the observations as part of scientific exchange programs. This collaboration educates the next generation of space scientists in the values and practices of international cooperation. Language differences are handled through specialized translation teams and real-time translation software during critical teleconferences. However, most technical communication occurs in English. which has become the de facto language of international space science collaboration. The data management systems developed for these observations incorporate international standards that allow access and analysis by scientists, regardless of their geographical location or institutional affiliation. This openness reflects the fundamental principles of international scientific research. The differences in national regulations on the export of scientific data have been harmonized through specific agreements for this project. Information that might normally be subject to restrictions is shared freely within the International Research Consortium. The data processing centers, located in different countries, use standardized algorithms and software to ensure that scientific results are reproducible, regardless of where they are processed. This standardization is crucial for maintaining scientific integrity in an international project. Coordination meetings include participants connected virtually from locations all over the world, using telepresence technologies that allow for real-time collaboration despite the geographical distances. These meetings operate across multiple time zones to accommodate global participants. The public communication protocols for the results have been coordinated between the public relations offices of the different agencies to ensure consistent and accurate messaging. Discoveries will be announced simultaneously in multiple languages and from multiple centers. The cooperation on the 3I divided by Atlas observations sets precedents for future interplanetary collaborations. The protocols developed, the lessons learned, and the relationships forged during this project will inform how humanity will approach future encounters with objects from other star systems. This international collaboration transcends temporary political tensions between nations, demonstrating how space exploration can unite countries for common purposes. In the cosmos, national borders disappear, and humanity works as a single, curious species, exploring the universe we all share. The success of this international coordination not only advances our scientific knowledge, but also strengthens the bonds between nations through the noblest enterprise of our species, the desire to understand our place in the wider cosmos. In the scientific libraries of the future, when science historians examine the turning points in our understanding of the universe, the coordinated observations of 3I divided by Atlas during October 2025 will hold a special place, not only as the first comprehensive, multi-instrument study of an interstellar object, but as the moment when humanity demonstrated that it could transform cosmic coincidences into revolutionary scientific opportunities. The legacy, immediate from these observations, is measured in terabytes of unique data that will fundamentally change how we understand objects that come from other star systems. But the most profound impact transcends any specific discovery about 3I divided by Atlas. It represents the maturation of space exploration as a truly collaborative and adaptive discipline. The methods developed to coordinate multiple spacecraft in simultaneous observations will establish the standard protocols for future interstellar encounters. The next time a stellar visitor crosses our solar system, we will no longer improvise ad hoc responses. We will have proven methodologies, established communication protocols, and international collaboration frameworks that can be activated immediately. The multi-instrument data processing techniques developed to integrate observations from Mars Express, ExoMars, Mars Reconnaissance Orbiter, and JUICE will create new paradigms in observational astronomy. These data synthesis techniques will find applications far beyond the study of comets, influencing how we approach the characterization of exoplanets, the study of hazardous asteroids, and the exploration of ocean worlds. The advances in space communications necessary to coordinate these observations will permanently enhance our operational capabilities in deep space. The data compression algorithms, adaptive transmission protocols, and temporal coordination systems developed for this project will benefit all future space missions. The educational impact of these observations will resonate for decades. Students of astronomy, space engineering, and planetary sciences around the world will study this event as a paradigmatic example of how modern space exploration can address complex scientific challenges through international coordination and technical innovation. The international GRAY collaborations forged during these observations have created professional networks that will continue to generate scientific, collaborative projects for years to come. The European, American, and other international scientists who work together on this project will maintain these connections, facilitating future collaborations that might not have otherwise existed. The data collected on 3I divided by Atlas will provide fundamental benchmarks for comparison with future interstellar objects. Each new stellar visitor will be evaluated against the detailed characteristics we have measured in this comet, allowing for evolutionary and comparative studies that will reveal the diversity of conditions in different stellar systems. The isotopic and chemical measurements of 3I divided by Atlas will influence planetary formation theories for generations. The specific ratios of different elements and isotopes measured by our spectrographs will provide calibration points for computational models of how planetary systems form and evolve throughout the galaxy. The insights on interactions between interstellar objects and the solar wind will improve our predictions about how future stellar visitors might affect our own solar system. This understanding will be crucial as we develop capabilities to detect interstellar objects with greater advance notice. The observation techniques developed for this project will accelerate the development of future missions dedicated to interstellar objects. Engineers are already applying lessons learned from these observations to the design of probes that could intercept or accompany future stellar visitors for extended periods. The success of international coordination during these observations will strengthen arguments for greater levels of international space cooperation in future projects. Policymakers have observed how technical collaboration can transcend geopolitical differences when focused on clear scientific objectives. The public communication protocols developed for this event will set standards for how the international scientific community communicates important discoveries to the global public. The coordination between multiple space agencies and academic institutions across different languages and cultures has created replicable models for future scientific announcements. The innovations in instrumentation developed specifically for these observations will influence the design of future space telescopes and planetary instruments. The modifications made to HiRISE to photograph fast-moving targets, the adaptations of spectrographs for cometary analysis, and the temporal coordination techniques will find applications in many other scientific contexts. The artificial intelligence algorithms developed for automatic data processing during these observations will establish new standards for automated scientific analysis. These computational tools will allow for faster and more comprehensive analysis of data from future missions, accelerating the pace of scientific discovery. The data archiving and preservation methodologies developed for this project will ensure that the observations of 3I divided by Atlas remain accessible to scientists for decades to come. Standardized data formats and comprehensive metadata will allow for future reanalysis as analytical techniques continue to evolve. The training programs developed to prepare international teams for these observations will become models for education in collaborative space science. Universities and research institutes will incorporate these pedagogical approaches into their graduate programs. The indirect economic impact of the technical innovations developed for this project will extend far beyond space exploration. Communication technologies, data processing algorithms, and coordination systems will find commercial applications that will benefit industrial sectors that are completely different. The case studies developed from these observations will inform theories of complex and international project management for decades. Business schools and engineering programs will use the coordination of the 3I divided by Atlas observations as an example of how to manage multifaceted technical projects under extreme time pressure. The philosophical implications of having observed successfully a fragment of another solar system in such detail will resonate across humanistic and scientific disciplines. Philosophers, theologians, and sociologists will examine how these observations change our perception of humanity's place in the wider cosmos. Perhaps the most important legacy of these observations is the demonstration that humanity can unite to study phenomena that transcend terrestrial borders. In an era of political division and international tension, the observations of 3I divided by Atlas show that we can collaborate effectively when we face mysteries that affect our entire species. In the coming decades, when other interstellar visitors cross our solar system, we will be better prepared thanks to what we learned during these days in October 2025. The observations of 3I divided by Atlas do not mark the end of a scientific adventure, but the beginning of a new era of coordinated and informed interstellar exploration.